So we'll talk now about word embeddings. So word embeddings is when we're actually in the realm of natural language. Let's say we have a dictionary of 10,000 words. That is, we just have a list, right, of all of our words in our corpus. So we've got dog, we've got cat, we've got hungry, we've got, somewhere a, the, and these are in no particular order, but we just know dog refers to, let's say, 1, index 1, cat is index 2. And so this is going to be all the way to 10K. And our last entry is going to be, so we have words coming in our X's. We've got some training instances that have words. Let's say we have a paragraph, and we are trying to determine the sentiment of the paragraph. That is, we want to know, is this, let's say it's a Yelp review. So is it positive or negative? Okay, that's what we're trying to do. So we've got a classification problem. Our input is going to be a Twitter post. And our output is going to be, we want to know whether it's, let's say this is about our brand or something. So we want to know whether it's positive or negative. So what can we do? Well, we know we have, 160 characters for our Twitter post. That's going to be at most, let's say, 75 words, okay, just as a rough order of magnitude. So what we could do is we could take a neural network and take in as input 75 words. How would we represent each word? We could represent each word as a 10,000 long one-hot vector. So we could basically have 75 1 by 10,000 vectors, which, as we went into the neural network, would just be a single 750,000 length vector. We should probably maybe add in one more here, which is something like not present. So that way, if we have a 5-word Twitter post, that says, I really like my Wheaties, then the remaining 70 words can just be not present. Well, this, if we go into a neural network, especially if this first layer is fully connected, this is going to be huge. We're going to have lots and lots of parameters. We'll need lots and lots of these Twitter posts in order, lots and lots of these labeled Twitter posts in order to actually train this network. So let's see whether we can reduce the size of this network in some way. Well, the way we can reduce the size is we'll go ahead and take in, so this is word 1, word 2, all the way to word 75. And we had just been concatenating these all together and putting them in the network. Instead, what we'll do is we'll feed them through E, an embedding matrix. So this one will come here and go out to there. And this will be the same. The key is all of these E's are identical. So remember that we can look at things graphically. We can also look at neural networks just as applications of functions. So what we were doing is we were saying that x equals all the way to x75. That is, we just had these all stacked together. And then we just said that z at 1 equals x w plus p. So this w is going to be some 750,000 by something matrix, depending on the size here. With embedding, we change it. With embedding, what we're going to say is basically x is going to first multiply each x1, each word, by this embedding matrix. And then the second word by the same embedding matrix, the second word by the same embedding matrix, and all the way through. So this now is smaller. If E is, let's say E is 10,000 by 50, then all of a sudden this becomes a 1 by 50 times 75. So 50 times 75 is around 25, 37, 50. So incoming to Z1 is now x, which is 1 by 3750, instead of 1 by 750,000. So this weight matrix becomes much, much smaller. So that's how you use an embedding matrix. And it can be trained just as normal, because really this is just part of the neural network. It's just sort of a layer 0 of this neural network, where here is the first layer of the neural network. The difference is that the number of connections here is much smaller than the connections would be if you went directly to the words. And so as we do training, we are training and adjusting the weights not only of sort of this part of the neural network, but also the embeddings. The single embedding matrix as well, because that's a key point here, is that it's the same embedding matrix. We're basically doing this conversion from a one-hot encoded word to a vector that represents that word in a continuous hyperspace. So we're going, when we go through the embedding, what comes in is one hot, and so this is discrete. And what comes out is continuous, lower dimension. And this is one hot, discrete, high dimension. Here, for instance, we don't have any measure of distance. We can't say, one of these vectors is closer than another vector. I don't have any idea, for instance, that dog and cat have some relation to one another. Yet, in this continuous lower dimension space, I might very well.